Hello everyone, my name is Zhao from Nanjing University, and today I will be talking about synthesizing ReLU natural networks with two hidden layers as barrier certificates for hybrid systems. This is a joint work with Xin Chen, Yifan Zhang, Meng Sha, Zhengfeng Yang, Wang Lin, En-Yi Tang, Qi Guangchen, and Xuandong Li. Before we dive into things, we should define exactly what we mean by safety verification on hybrid systems. The hybrid system consists of a group of continuous systems. A continuous system pi is composed of x, f, d, and I, where x is a set of system variables, f is the vector field over system variables x, d is the state space of x, and I belongs to d is the initial states. A hybrid system contains several modes, and each mode is a continuous system. In detail, a hybrid system is composed of M, X, F, D, I, T, R. M is a finite set of modes. X is a set of system variables. F is a set of vector field. D is a state space. I belongs to D is a set of initial states. Above elements are the same as those in continuous system. Especially, system states can transit between different modes. T and R denote transition states and reset function. We display a hybrid system containing two modes. Each mode is a continuous system. The vector field of the hybrid system is there. When system state transits between two modes, the reset function will be applied on each system variable. The safety verification of hybrid systems is to determine whether the system trajectories from some initial states can reach the unsafe region. There are various solutions to this problem. They are roughly divided into two categories. The one is based on reachability analysis. The key idea is to compute the reachable set or its over approximation for each time step t and ensure the reachable set doesn't intersect with the unsafe region. Since those methods need to compute the reachable set step by step, the computational complexity is relatively high. Besides, they can only verify the safety in a finite time and can hardly be used in an infinite time. The other category is based on barrier certificate. A barrier certificate is a function that separates reachable set from the unsafe region. It requires a system trajectory starting from the initial states to fall into one side of the barrier certificate, while the unsafe region resides on the other. As the instance of a barrier certificate proves that the unsafe region is not reachable, the safety verification problem can be transformed into the problem of barrier certificate generation. Then, the problem is how to find a barrier certificate. We first talk about the conditions that a barrier certificate should satisfy. Given a continuous system pi and the unsafe range U, a barrier certificate B is a function satisfying three conditions. The first condition, for any state x belonging to unsafe range U, Bx is greater than 0. The second condition, for any state x belonging to I, Bx is less than or equal to 0. The third condition, for any state x, if Bx equals 0, the derivative of Bx to x multiply Fx is less than or equal to 0. The first and second conditions require B is positive and non-positive on the unsafe region and the initial states, respectively. The third condition implies during continuous flow, Bx cannot be a positive state. That is, the system trajectories will not cross the line Bx equals 0 to reach the unsafe region. If all three conditions are satisfied, B is a barrier certificate of system pi, and pi is safe. Now we consider the barrier certificates for hybrid systems. A hybrid system consists of a set of continuous systems. Correspondingly, the barrier certificate is a set of functions satisfying the four conditions. On each mode, For any state x belonging to IC fringe U, Bx is greater than 0. For any state x belonging to I, Bx is less than or equal to 0. For any state x, if Bx equals 0, the derivative of Bx to x multiply Fx is less than or equal to 0. The three conditions are similar to those for continuous systems, especially when transiting between different modes. The fourth condition requires Bx cannot become positive if it is non-positive before transition. If all four conditions are satisfied, B is a barrier certificate for hybrid system pi, and pi is safe. Then, for the problem of how to find the barrier certificate, this work adopts natural networks to represent barrier certificates. The natural network N is a tuple L, W, B, phi, and X. L is a set of layers. L0 is the input layer, Ln is the output layer, and others are hidden layers. Layer Lk has SK neurons. W is a set of weight matrices. B is a set of Bios vectors. Phi is a set of activation functions for hidden layers. X is a set of layer neuron outputs. For each hidden layer, let Zk denote the neuron value before applying activation functions. The forward propagation of natural network is pushed forward by layers. The output of the preceding layer is the input of the next layer. In each hidden layer Lk, Zk equals Wk multiply Xk minus 1 plus Bk. Then applying activation function phi on Zk to get Xk. The natural network output is the value Xn. Now we introduce our approach to synthesizing natural network barrier certificates. The natural network needs to be trained on the training datasets to satisfy the barrier certificate conditions. We generate training datasets based on the hybrid system and construct the loss function. Then we train the natural network. The structure of natural network used in this paper has two hidden layers, and the activation function is ReLU. ReLU is defined as if x is greater than 0, ReLU x equals x. Otherwise, ReLU x equals 0. After we finish training, we get a candidate natural network barrier certificate. Since the candidate is trained on the training datasets, it may not be a real barrier certificate for the whole hybrid system. We need to verify whether the candidate satisfies the barrier certificate conditions or not. For verification, we code barrier certificate conditions into a set of MILP and MIQCP optimization problems, then solve them using numerical solver with formally gradient results. If we get expected results, the candidate is a real barrier certificate and the hybrid system is safe. Otherwise, the solver will return some counterexamples. Those counterexamples do not satisfy the barrier certificate conditions. We add them to training datasets and retrain the candidate. Now we talk about how to train the candidates and verify it in detail. The natural network receives an input x and outputs bx. The input x denotes the state value of hybrid system, so the neural number of input layer is the same as the number of system variables. There are two hidden layers. Each layer has an arbitrary number of neurons. Each neuron is accompanied with a ReLU activation function. The output layer has one neuron, denoting the barrier certificate output Bx. To train the candidate natural network barrier certificate, we need to generate training datasets. We generate 4 datasets corresponding to 4 barrier certificate conditions. The first dataset contains the points sampled from IC region. The second dataset contains the point sampled from initial states. The third dataset contains the points satisfying Bx equals 0. Since the parameters of barrier certificate is always changing in training, we sample points from system state and test them in real time to pick those points satisfying Bx equals 0. The fourth dataset contains the points sampled from system trajectories. The evolution time of trajectories is long enough to cover the transition states. For the third dataset, the constraint Bx equals 0 is too strict. We relax it using a positive number option. Then, the points in second and fourth datasets have the same output Bx is less than or equal to 0. We merge them into one dataset. Now there are three datasets. We construct those functions based on them. For the points in the first dataset, the barrier certificate output Bx should be positive. Otherwise, it will produce loss. Let it be a positive number. The first part of loss L1 is defined as for any points belonging to D1, negative mean nx minus eta 0. The second part and the third part of loss are similar. Then the overload is a combination of three parts. We minimize the overload to get the candidate neural network barrier certificate. The candidate is trained on the training datasets, so we need to verify whether it is a real barrier certificate for the hybrid system. We consider four barrier certificate conditions for the trained neural network. Since the neural network output Bx equals the output layer value x3, the conditions need to be verified transformed as for any x0 belonging to U, x3 should be greater than 0. For any x0 belonging to I, x3 should be less than or equal to 0. For any x3 equals to 0, the derivative of x3 to x0 multiply f x0 should be less than or equal to 0. For any x0 belonging to transition state t, if x3 is non-positive, after transiting and resetting, x3 apostrophe should be non-positive. The first, second, and fourth conditions involve the neural network output. The third condition involves the neural network derivative. Now, we verify the first condition. Recall the neural network for the propagation. We construct the optimization problem P as minimizing x3 subject to x0 belonging to U for k equals 1 or 2. Zk equals wk multiply xk minus 1 plus bk. Xk equals ReLU zk. X3 equals w3 multiply x2 plus b3. If the minimum value of the problem P is greater than 0, for all the points belonging to IC region U, the barrier certificate output x3 is greater than 0. Then the first condition is verified. For the constraints in this problem, ReLU is nonlinear and needs further recording. For ReLU, we adopt the MILP encoding method. With the help of binary variable t, the behavior of x and y in the MILP coding is the same as that in ReLU. Then ReLU is represented as a set of linear and binary constraints. Besides, there may be some nonlinear functions when representing the IC region U. For those nonlinear functions, we adopt the piecewise linear approximation method to approximate them. For a nonlinear function gx with xe, lx, ux, it can be approximated by two piecewise linear functions glx and gux, where the difference between glx and gux is not greater than a controlled approximation error delta. Then the problem P is transformed into P1, mean x3, subject to x0 is greater than or equal to gl and less than or equal to gu. This constraint is used to limit x in the IC region. Zk equals wk multiply xk minus 1 plus bk. This constraint represents the neural value before applying activation function. Then, the following 5 constraints are the MILP coding of ReLU. The last constraint x3 equals w3 times x2 plus b3 represents the neural network output. Because of the approximation, Py is a superset of P. That is, Py is less than or equal to P. Then, if the global optimum Py is greater than 0, P is also greater than 0. For any x0 belonging to U, x3 is greater than 0. Then the first condition is verified. However, find the global optimum is difficult. Instead of directly finding the global optimum, we determine the sign of the global optimum based on the current optimum. When solving problem P1, the solver will return a current optimum P apostrophe with the maximum relative error C defined as this. If C is less than 1, the global optimum P star and P apostrophe have the same signs. Then, if current optimum P apostrophe is greater than 0 with C is less than 1, the global optimum P star is greater than 0 too. For any x0 belonging to U, x3 is greater than 0. The first condition is verified. The verification of second condition for any x0 belonging to I, x3 is less than or equal to 0 is similar with the first one, except for the input and output of the natural network. The verification is transformed into the problem P. When solving this problem, if the current optimum P apostrophe is less than or equal to 0 with C is less than 1, the global optimum P star is less than or equal to 0 too. Then, for any x0 belonging to I, x3 is less than or equal to 0. The second condition is verified. The verification of first condition is also similar and is transformed into such a program. The left part equals the natural network behavior before transition. The constraint W3 multiply x2 plus B3 is less than or equal to 0 limit the natural network output should be non-positive before transiting. The right part equals the natural network behavior after transition. The objective of the problem is x3 apostrophe, denoting the natural network output after transition. We verify x3 apostrophe is non-positive when transiting from a non-positive state. When solving this problem, if the current optimum P apostrophe is less than or equal to 0 with C is less than 1, the global optimum P star is less than or equal to 0 too. Then the first condition is verified. Now we consider the third condition for any x3 equals 0. The derivative of x3 to x0 multiply fx0 should be less than or equal to 0. The derivative should be computed. According to the natural network forward propagation, the backward propagation is defined as the derivative of x3 to x2 equals w3. The derivative of xk to zk equals the derivative of phi k zk. The derivative of zk to xk minus 1 equals wk. Applying the derivative chain rule, the derivative of x3 to x0 is computed by w3 multiply derivative of phi 2 z2 multiply w2 multiply the derivative of phi y zy multiply wy. Now we consider the derivative about the activation function ReLU. Let Rx be the derivative of ReLU x. If x is greater than 0, Rx equals 1. Otherwise, if x is less than or equal to 0, Rx equals 0. Observing the MILP coding of ReLU, we can find if x is greater than 0, t equals y. Otherwise, if x is less than or equal to 0, t equals 0. The value of binary variable t is the same as Rx. By replacing Rx with t, the derivative of x3 to x0 is computed as w3 multiply t2 multiply w2 multiply t1 multiply w1. w3, w2, and w1 are constants. t2 and t1 are variables. So this computation is a quadratic function. Then the verification is transformed into such a problem. Let's first look at the constraints of this optimization problem. The first constraint defines the region of x0, and then the following constraints encode the behavior of the natural network. The penultimate constraint restricts x3 to 0. The last constraint represents the derivative of x3 to x0. The objective of this problem is the v multiply f x0. There may be some nonlinear functions in f x0. We approximate them using piecewise linear functions. Then we can consider fx is linear. So the objective is quadratic. This problem is a MIQCP problem. When solving this problem, if the current optimum P apostrophe is less than or equal to 0 with C is less than 1, the global optimum P star is less than or equal to 0 too. Then the third condition is verified. Now all the four conditions are verified. If we get expected results, the candidate is a real barrier certificate and the system is safe. Otherwise, sample data points around counterexamples and add them to the corresponding training data sets to retrain the candidate. We implement the barrier certificate synthesis tool named SensorBC and compared it with two state-of-the-art methods, N-barrier and SOS method. SensorBC uses natural network barrier certificate with ReLU activation functions. It calls the barrier certificate conditions into optimization problems and solves them with a numerical solver. N-barrier uses natural network barrier certificates with bent ReLU activation functions and verifies barrier certificate conditions using SMT solver. SOS method uses polynomial barrier certificates and it doesn't need verification. The examples include 3 hybrid systems and 8 continuous systems. The functions in vector field include polynomial, square root, sine, cosine, exponential, and so on. The system dimension is up to 12. For all 11 examples, SensorBC verifies 10 examples, while N-barrier and SOS method verify 4 and 5 examples, respectively. Both SensorBC and N-barrier use natural network barrier certificates. The training and verification time of SensorBC is much less than N-barrier. Those experimental results show that SensorBC is more scalable and effective than N-barrier and SOS method. Conclusion of this work, we adopt ReLU natural networks with 2 hidden layers to synthesize barrier certificates for hybrid systems and transform the problem of verifying barrier certificates conditions into a group of MILP and MIQCP problems. We develop an optimization-based technique that takes advantages of the current optimum to identify whether the candidate barrier certificate is a real one. We implement the tool SensorBC and evaluate its performance over a set of benchmark examples. The experimental results show that SensorBC is more scalable and effective than the existing methods. That's all. Thanks very much.